Hello everyone, this is Nathaniel Stemman presenting on setback distances for natural gas pipelines in the United States. To begin with, I first want to define what a setback distance is, which is the minimum distance from the target building to the center line of a pipeline. This is a policy that falls under land use, so it is under the jurisdiction of local municipalities such as counties and cities. And as you can see here from the chart, the setback distance ranges from anywhere from 15 meters to 152 meters. And in addition to this, there's also a lot of municipalities that do not even have setback distances, which is due to a lack of data and lack of research available for policymakers and voters to understand the situation at hand. Setback distances is an emerging policy due to the increased pipeline and human interaction that we've begun to see in the last few decades. And the reason why there has been this increased interaction is due to urbanization and the increased energy demands. This increased urbanization has created this increased interaction due to humans now living in once rural areas where these pipelines were originally laid down. And we're starting to see these consequences as seen in the accident in Firestone, Colorado in 2017, where a pipeline was damaged during the building of a particular home. And over 2 years, this pipeline leaked enough methane into the home, which resulted in an explosion and unfortunately fatalities. So the objective of my research is to understand the soil properties and their influence on this natural gas migration through the usage of vapor intrusion models to aid in the development of these setback distances. The model in which I used was the PVI 2D model, which is a two-dimensional analytical model that considers diffusion to be the dominated factor of transport. The chart under section 4 is the default values that I used in order to run my simulations. So the first simulation that I ran was over permeability because I wanted to see how soil types, which is related to permeability, affects the vapor transport flow. The first figure under section 5 is the concentration gradient using the sand as the soil type at 1 meter depth, which shows high concentrations throughout the subsurface, reaching 30% of the original source just 0.1 meters below the surface. And this also shows the highest amount of indoor air concentration. In the second figure, I showed the comparison between sand versus 5 other different types of soil. And they range from anywhere from sand to sandy clay loam to loam. And as you can see here, sand has the greatest permeability in comparison to all other soil types. And we also saw a highest indoor air attenuation, which is the ratio between indoor air concentration of the contaminant, which is methane, over the contaminant source concentration. So we can see there is a positive linear relationship between permeability and indoor air concentration. Did another simulation on the depth of the contaminant using sand, and we can see that as the depth of the contaminant increases, the indoor attenuation decreases, which is expected. But this decrease in the indoor concentration results in the concentration of the methane now being between the upper explosive limit and lower explosive limit of methane, which is of concern for practitioners. So in conclusion of my research, I found that even though that sand has the greatest permeability, which allows for the most amount of movement of the methane from the source to the subslab of the building, and if we increase the depth of this pipeline or this source, the concentration will then fall. We also have to make sure that we are not allowing this this depth to then be able to fall within the explosive limits of methane. And so in my future work, I hope to explore the building properties of concern to look how the building properties affect the transport of methane from the subslab to the indoor air. I would like to conduct interviews with the stakeholders of concern for this. And finally, I would want to conduct field experiments to verify my modeling results.